Well, greeting to my lecture. Today I'm going to present about computer-aided engineering, MMK21103, for a presentation purpose. My name is Varshini Ravindran and my metric number is 251324068. So my project is actually a table, okay, drawn in CATIA software and analyzed using NSE software. It is a tabletop, a stand, a table connector, and a bolt that actually goes in. I have three models. First is the original design using structural steel completely for the table. Second is modification number 1. I've changed the material into titanium alloy. The third one is modification number 2, where I reduced the thickness from 10 mm to 8 mm for the tabletop. So these are the objectives of my product. First is to analyze and to compare the mechanical behavior of structural steel and the titanium alloy for modification number 1 under the same loading conditions, and the load is actually 300 Newton. And the second objective is to assess the effect of thickness reduction on stress distribution, deformation, and safety factor, which comes under modification number 2, where I reduce the thickness. The third is to determine whether the modified design actually meets the structural integrity requirements, okay, while achieving the weight reduction. Does it actually reduce the weight? And the last objective is to identify the potential changes, okay, related to material substitution and geometric modification using finite element analysis, which is FEA in NSE's workbench. So these are the objectives. My problem statement is, can titanium alloy actually provide equal or better structural performance compared to structural steel at a reduced thickness? Can it actually provide a better structural performance compared to the structural steel? Okay. And then second one, does reducing the thickness from 10 mm original design to 8 mm compromise the strength or safety of the table? Is there any changes? And the last problem statement would be, what trades-off exists between the weight reduction and the structural stability in the modified design? Now we are going into introduction. First, we would know that structural steel is actually widely used, okay, because of its higher strength and lower cost in the industry, okay, because it increases the structural weight due to high density. So structural steel is very high in density, so it can increase the weight, so it is way more safe. This project replaces structural steel with titanium alloy, okay, to reduce the thickness, and that's the first modification. And the second one is to reduce the thickness of the tabletop, the top design, from 10 mm to 8 mm to improve strength to weight efficiency, okay, because the weight is actually reduced. Third one, static structural analysis using NSE's workbench evaluate stress, deformation, and factor of safety. So this analysis is actually using static structural. Okay, so I can analyze the stress, one misses, total deformation, and safety factor. The study actually focuses on modeling and comparative analysis, excluding manufacturing cost and experimental testing. It's only for the analysis purpose. Literature supports material substitution and thickness optimization using FEA, finite element analysis, for safe weight reduction. I'd like to explain the steps, okay, in a very brief way. First, we have to draw the parts in CATIA. Okay, so I've drawn the bolt, the stand with a hole using the CATIA software, and then a connector that actually connects the stand and the bolt, and then a tabletop. And I've done assembly for all of this to actually create a table. Okay, so that's the first step. Second, I've opened the NSE's workbench software to analyze, okay, to get the 1 meter stress, total deformation, and safety factor. So the first step is to actually do material assignment. Okay, I've select all of them, okay, using body icon, and assign the material, which is structural steel. Okay, and then I would like to I did the boundary conditions, and before boundary conditions I did the meshing. Okay, I've set the meshing element as 5.0 mm for the whole table, and then I set the boundary conditions. The fixed support is at the connector, the table connectors, all the faces of the table connectors, and my force is 300 Newton on top of the table. It's facing downwards to the tabletop. And then I've added safety tool, stress von Mises, and total deformation to obtain the results. I solved it and I got the results. This is for original design. For modification, I did the same, but in the engineering material, which is the material assignment, I didn't use structural steel, but I used titanium alloy. For the third modification, for the second model, for the second modification, but the third model, what I did, I reduced the thickness. Okay, in CATIA software, I redraw the tabletop from 10 mm thickness, I reduce it to 8 mm. Okay, so when I put it in the analysis book, which I did everything the same, and I also use structural steel. Okay, because we can compare with the reduced thickness, but the same material, what is the results obtained. Okay, so this is model number 1, which is the original design. As we can see, the total deformation is 0.36932, and this equivalent von Mises stress is 74.337, which is actually quite high. Okay, 74, and the safety factor is 3.3631. It is actually safe. Okay, above 1 it is safe, under 1 it's not safe. So this table is safe, but I would like to modify it in a better way to increase the safety factor. Okay, so this is the second model or the first modification. Okay, so we can see the table total deformation is 0.09412, and the stress is 34.561, which is very much reduced from 74 to 34. It is reduced in 40%. I mean in 40, in number 40, not percent, 40. And the safety factor is 15. The 15 is actually the maximum safety factor. So when we replace it with titanium alloy, it is very much safe compared to structural steel. Okay, so this would be modification 2, okay, or the third model. The total deformation is 0.047117, and the stress is 38.496, which is actually good. Okay, it is reduced from the first one. The first one was 70 something, and this one is 38. And then the safety factor is 6.4942, which is safer than the first one also. Okay, because the first one was 3 point something and this one is 6 point something. So the safety factor has been increased, which is a good sign. Okay, so this table is modified, and this one is the reduced thickness from 10 mm to 8 mm. As you can see, this is the graphs. Okay, for the total deformation, the original is higher, the modification is in the middle, and the modification 2 is very low. The one with the stress, as we can see, the original is the highest one. So the modification 1 and 2 is modified in a better way. Safety factor, the modification 1 is the highest, okay, because it's 15, and modification 2 is in the middle, which is 6 point something, and for the original it's 3 point something, so it's the lowest. Explanations for the modifications. Original design, which is a structural steel with 10 mm, was structurally stable with stresses below the yield strength. High stiffness resulted in low deformation and a high factor of safety, but increased the overall weight. So improved design using titanium alloy with reduced thickness 8 mm to achieve weight reduction. Maximum stress increased due to thickness reduction but remained within allowable limits. Deformation increased because titanium alloy has a lower elastic modulus. Overall, the improved design achieved better strength to weight efficiency without compromising safety. Okay, so the first modification, which was the material substitution, and the second one for the thickness, is actually good. Finally, the conclusion. Okay, so the original design, as I said, the stress is actually higher. The safety factor is lower compared to the modification 1 and modification 2. Okay, because in the modification 1, the safety factor has increased to 15, which is very excellent, and for the modification 2, it improved overall load distribution, okay, which was 300 Newton due to reduced thickness. That's all from me. Thank you very much.